For example, teachers and students, or say hospital and patient, maybe college student. Okay, so in theoretic uh, nomenclature, we often say that it's a case of bipartite graph, where the graph can be partitioned into two components. Okay, and there are connections between the elements of the left side and the elements of the right side. Of course, I mean, among the elements of the left side, there is no connection. Okay, similarly for right side. So it's a case of bipartite graph. Okay, now to give an example, so of course, I mean, uh, there are variations in this matching. Like suppose I can assign. Let us take a particular example that will make it clear. Okay, let's say I mean student and teacher. So one student is going to be assigned to a teacher, or multiple students are going to be assigned to a single teacher. Okay, when a student is assigned to a particular teacher, we draw a imaginary line between the student and the teacher, indicating that there is a connection between them. Okay, now with this thing in mind, we can probably assign every student to exactly one teacher. Okay, but it may so happen that one teacher actually is getting many students. It may so happen. So it's a different kind of assignment, but we are not going into that. We want an assignment where one student is assigned to exactly one teacher. That means if a student teacher pair occurs in an instance of the matching, neither of them actually can occur in any other instances. Okay, that's the definition of matching actually, where an instance of student or teacher cannot repeat more than one. Okay, remember how many times it occurs in a matching, either 1 or 0. So if a student cannot find a proper match, then it remains unmatched. Okay, then we say it's okay, then it's just a matching. But when it is the case that every student gets exactly one match to one teacher, and every teacher is also matched to exactly one student, okay, this situation is very much desirable. Okay, and this kind of matching where exactly one occurrence of student and a particular teacher happens in the match, then that matching is known as perfect matching. So, uh, so one question can be that what do you understand by perfect matching? Okay, this can be a potential question. Okay, so what is perfect matching in a bipartite graph? Remember, if this question is asked, then probably the answer should be that you have to draw a graph and you have to explain what is a perfect matching. You have to draw a bipartite graph and you have to explain the matching. What is perfect matching? To have perfect matching in a bipartite graph, Of course, the two parts, left part and the right part, must have identical number of elements, say n and n. If the left side has n, the right side has m, but m is not equal to n, then of course the smaller of them, let's say n is smaller, then the matching size will be n, and certain number of elements in the right side will remain unallocated or unmatched. Okay, so in that case, the matching, there exists a matching, but the matching is not perfect with the given input, because all of the teachers are not allocated. Some teachers are remaining empty. They have no student actually. Similarly, if some student do not get a guide, then that's also not a perfect matching. Okay, so there is this concept of normal matching, where the occurrence of an item can be at most one. That means 0 or 1. But perfect matching requires the occurrence of an item is exactly once. Okay, that should be clear. So given that situation, let us assume for the time being that there are n students and n teachers. Okay, two sides of a bipartite graph. Now, how we can match them? Okay, we can make a just random match. Okay, randomly we can assign any student to any teacher, and we just need to check that they do not, occur more than one. Okay, that means only there is one such pair. Okay, I mean one student SI and one teacher, suppose TI. I mean there is exactly one occurrence of TI in the entire set. Okay, there is exactly one occurrence of SI in the entire set. So that means you can think of mathematically a matching is a matching is actually a subset of S T cross S. T cross S means all possible pairs of the form, a perfect match, I should say. Perfect match is of the form of a subset of S T cross S. Capital T is actually suppose T1, T2 up to Tn. Capital S is actually up to suppose S1, S2 up to Sn. Then T cross S is actually of the form x comma y, where x is from T and y is from S, right? So this means all possible pairs. There are repetitions actually. One element can occur many times. So therefore, the matching is actually subset of this T cross A such that the occurrence of each Ti is exactly equal to 1. Similarly, the occurrence of each Si is exactly equal to 1. So it's a proper subset of T cross S satisfying certain conditions. Now, as I was saying, that we can make a random connection that satisfies this condition. Okay, the way we like. Okay, so if the teacher and the students are okay with this random configuration, then probably we can do this matching in how much time? Linear time, right? Because I need to assign one student to one teacher. So what I will do, a naive algorithm, like I will pick one random student and I will pick one random teacher. I will just make them pair and I'll put them in the match set. A match can be thought of as a bucket. Okay, I'll put that pair in that bucket. Okay, so I'll randomly pick the next student. I'll randomly pick the next teacher, and I'll pair them and put them in the bucket. This thing, if I just do n times, then my bucket will become full of n pairs. And there are actually n students and n teachers, and somehow they're matched, right? Everybody agreed? This is a simple way to match. Okay. Without any condition. I mean, if the student goes to any teacher, he's more or less happy. The teacher, as long as he gets exactly one student, he is happy. Uh, so without any condition, this perfect matching between n students and n teachers that can be done in order of n time, where n is the size of the input. Okay. Size of the input means one side, basically. So the problem starts when, if it so happens that in this match, in this bucket, I have n such pairs, and I have two such pairs. Let's say I have two such pairs, like say T1 S1 and T2 S2. Okay, I have two such pairs, T1 S1 and T2 S2. Okay. So what is the condition is I have done the matching in a random way and I feel it's fine. But suppose if there is some preference among the teachers and the student. Okay? Preference means I like to go to that teacher or I like to have that particular student. So if this kind of preference. Okay? Or ordering among the students. So as a teacher, there are n students, I can have one particular permutation of the students, n students, that is the best choice for me. So given n students, I can have n factorial permutations of the students. Out of n factorial, one particular permutation is the most preferable for me. That means I would like to get that particular student as the first choice. If not, I will like to get the next one as the second choice. If not, I'll like to get that another student as the third choice, like that. And so on, I will have a ordering of among the n students. Okay. Remember, each teacher is an individual entity. So each teacher will have his own ordering of the students. Teacher 1 may think that okay, S1 is best for me, so he can put S1 in the first place. But teacher T2, he or she may not put S1 in the same place. He may put S1 at somewhere in the middle or at the last. Okay, so it is a person to person choice. So if you think this way, then that information that ordering of n students is one particular permutation that is stored with a particular, suppose that is stored with a particular teacher. So that needs, suppose, an array or vector of space order of n. Because I'll put some, I'll put the first element, first student in the first place. I'll maintain an ordering of the students. Okay. So one teacher needs a size of a vector of order n. So there are n teachers. Each will individually like to store that vector. So you need basically n vectors to represent the choices of the student. Okay, so you can think of it's a n vectors each with size n, or you can think of it's a n cross n matrix. Okay, where the rows corresponding to the teachers and the columns are actually the student preferences. Now this similar thing can happen to the student as well. I mean, one student, after coming to the department, he to under whom he will do his BTP or suppose MTP or PhD, there is a list of teachers, and he, through some background information and etc., he has that information that okay, I have n teachers. This is my first choice. This is my second choice. This is my third choice, and so on. So, among the teachers, he will have one permutation of the teachers and he will like to store that with him. Okay. So likewise, I can say that every student has a vector of size n and there are n students. So there are n such vectors basically. So uh, it is actually another matrix that is again n cross n. Okay. Remember here why we are uh, interested in keeping the number of students and teachers equal, because we are interested in stable matching and perfect matching. Oh, okay. Let's forget the stable matching, perfect matching. We are interested in perfect matching, right? So initially, when we did random assignment, then it was a match, okay? But now with this, it was a perfect match without any condition. But now if this preference comes into the business, then probably such a random matching will not work. Why it will not work? That I give an example. Okay, let's say there are I have the random matching in my bucket. Okay, in such pairs, and somehow I find two pairs like T1S1 and T2S2. Okay, and somehow T1 finds that I am currently attached to S1, but I like S2 more than S1. Okay, so T1 has a vector, and in that vector, S2 comes before S1. That means actually T1 prefers S2 more than S1. Similarly, S2 has a vector of all the T's, and S2 finds that in my vector, T1 occurs ahead of T2. Okay. So understand this situation. It is like this. If you can look at this picture, okay. So T1 is assigned to S1, T2 is assigned to S2 by the algorithm, but according to the vector, T1 has S2 ahead of S1 in its vector, whereas S2 also has T1 ahead of ST2 in its vector. Then what will happen? T1 and S2, they know that they both will be benefited if they leave their current pairs and they make a new pair. They both will be benefited. Okay? So then what will happen? They will leave their current pairs and they will make a new pair like T1, S2. Okay? They will make a new pair because they both find it to be benefited. So what will happen then? The happening is S1 will remain unmatched and T2 will become unmatched. Then there should be somebody uh, who has to match them. That is number one. The number two is this kind of situation where T1 and S2, they feel that if they make a pair, both will become benefited. This kind of situation is known as a blocking pair. Okay, this situation is known as a blocking pair. So if blocking pair happens to exist in my random matching, then my matching, I mean, the blocking pair actually they will pair together and they will make others unmatched actually. So I then have to go to the bucket, I have to match them. Okay, something like that. So blocking pair, existence of blocking pair is not desirable. Okay. Or this is in the language of matching, this is also known as instability or unstable match. If there is a blocking pair, at least one blocking pair, then it's an unstable match. Now, so what can be the question here? The question is, what do you mean by a blocking pair in a stable match situation? Okay, then the answer should be, you should start with, okay, that every teacher has a vector representing the preference among the students. Every student has a vector of teachers representing the preference among teachers. And then you define with a picture that what is a blocking pair. And then through that example, you show if such a blocking pair happens, what problem can occur. Okay, so you should not have any blocking pair. Remember here, if you can see this picture, in the blocking pair means both can improve their situation. It's not like, I mean, if one can improve its situation and the other cannot, okay, then that's a blocking pair. It's not like that. So suppose there is I put a link in this left side, So that means if T1 finds that in its preference list S2 has a higher preference than S1, but S2 finds that in its vector T2 comes ahead of T1. That means it doesn't find any improvement. Okay. Then just one-way arrow, one-way line, one-way improvement doesn't mean it's blocking pair. Because both are not finding any benefit to pair actually. So then it's not a blocking pair. But if both finds such a benefit, so both way arrow I can draw, then it's a blocking pair. So now I have done a random matching. I do not know how many blocks, given such a vectors of preference or matrices of preferences, I may like to get rid of all such blockings. And remember, I mean, Suppose I do it like this, that I do a random way of matching so that it becomes a perfect match, but I don't know whether it's stable. So another question is, what is a stable match? What is a stable matching? The stable matching is a matching where there is no blocking pair. Okay. Stable match is a matching where there is no blocking pair. So if you are asked this question, as I told in the last class, we have to solve all these questions. So if the question is, what is a stable matching problem, or what is a stable marriage problem? It's sometimes called stable matching, stable marriage, synonymous. So what is a stable marriage problem? Then you have to give a bipartite graph picture, and you have to number them, say TISI, or suppose W1 to WM, M1 to MN, women and men. So for marriage it comes to men and women, and for some other problem it comes something like that. And you have to say that what is a stable matching. Stable matching is, you will find a bucket of n pairs such that take any possible uh, pairs, any possible two elements. I mean, any possible pairs you take from that bucket, you cannot find a blocking pair. Okay? You cannot find a blocking pair. That means nobody will unilaterally like to change its partner. Nobody will find. I mean, remember, what is a blocking pair? Two people will leave their current partner and join to make a pair only if both find that it is beneficial for both of them. If one finds that it is beneficial for me, but the other does not find, then they will not join. It's like simple marriage actually. So a match where there is no blocking is known as a stable matching. Now, as we know that for a random perfect matching, I can do in linear time, O of n time. Okay, because I just do one by one like that. But how can I, given this input? So given this input, what is the input? You have a bipartite graph with left side and right side. If we can take an example like men and women or student teachers. And left side has this n elements, right side also has n elements. Also, you have these matrices of preferences. Each teacher has a vector of the n students. And remember, this vector may or may not be same. Okay. Another point I will make you, I'll make a point here, is that someone may say, okay, one teacher need to have a vector of the n students, and I do not need to fill the entire vector. Let us not go into that direction, because then the preference is partial. Partial means I only care about the first, say, 50 students. I do not care about the remaining 50 students. But that does not mean you will not give any preference to them. I mean, you cannot give partial preference list. You have to give a full preference list. Okay. The question may arise that what will happen if partial preference list is given? Then the problem will change drastically. We are not going into that detail. It's a totally different problem. For the sake of simplicity, we assume that everybody gives a complete preference list of n elements, n students or n teachers. Now, with that in hand, how can I think of design a matching which will be stable? and perfect. Of course, it will be perfect because there are an equal number of elements. But how can we ensure that it is stable? That means there will be no blocking pair. Okay? One can think of a naive algorithm like this, that I will first make a random matching that will take order of n time, because I just pick one random teacher and random student and I pair them and then I put aside. Then what I will do, as I keep on, I have formed a random match, then I take one pair, okay, and I check whether there is any instability or there is a blocking pair in this pair of pairs, okay, in this, I mean, between these two such tuples, uh, two such pairs, is there any blocking pair or is there any instability? If it is there, then what I do, I mean, rewire them. That means I just remove them and reassign them in such a way that the instability goes away. Okay, but and I keep on doing like that. So the problem is that I mean, given n such pairs in the bucket, I have to choose two pairs. Okay, so there are n choose two possibilities. Okay, then it may apparently look that, okay, by n choose two possibilities, if I think that there is no such instability, then probably I can solve the problem. But it may so happen that after, due to the removal of instability between a uh, pair of elements, I actually introduce an instability in somewhere else. Actually, it may so happen, and this may actually occur in a cyclic manner. Okay, cyclic manner. That means I remove the instability here, I remove the instability there, but again another new instability comes in. So if it so happens